Good afternoon, one and all. So let us begin with our topic for today, which is advanced data processing techniques in geosciences. So first, you know that in geosciences, different types of data is used, right? So first we have remotely sensed images, and we have data which is obtained via ground truth correction. So what is an image basically? An image is an artifact that depicts visual perception of an object or scene. So images, there are two types of images. One is an analog image and the other is digital image. The difference is that analog image will give you continuous levels of brightness, okay, whereas digital image is a matrix of small elements with a unique value. So basically it's a multi-dimensional array of numbers, right? So if you take this image and if you take a small part of that image, each of the component will be composed of three sets of matrices, and each of the particular location will have a single number associated with it. So each pixel will be associated with a finite or discrete quantity of what? Of its intensity, gray level, digital number, brightness value. So all of these mean the same thing. So and there is that we use. So these types of data I will be talking about, and the techniques, the advanced techniques that I will be discussing are principal component analysis for images and for data, and image segmentation techniques, as well as watershed transform techniques for images. So let's get started with the first topic, which is principal component analysis. So basically, how does principal component analysis work? I will tell you in detail, and I will explain the basics which are associated with this topic. So if you are not already familiar with the geostatistical concepts of different variables, mean, variance, standard deviation, covariance, I will briefly discuss that also. So let me first start by saying that the first step is to collect your data. If you have to collect ground truth data, or if you have to collect the remotely sensed images, then the next step will be to create a spatial data set. It will not be required for remotely sensed images. So basically, variables are nothing but the properties of the geospatial data that you will consider, and the samples are nothing but the different rock samples that you have at different locations that you have collected, or they will be nothing but your pixels. So basically, for any variable that you consider, you have to first standardize that. And in most softwares, there's you just have to click some buttons, and then that entire process is automated. However, I want to explain the basics behind it, or what goes behind the PCA method that we mostly just use without understanding. So firstly, the step is to standardize any variable that you use, which is done by subtracting it by the mean and then dividing it by the standard deviation. So mean, as you all know, it's nothing but the summation of all of the variable values, and you divide it by the total number of observations. That is summation I1 from n 1 to n xi divided by n. Then standard deviation is another is a square root of this quantity. And if you take a square of the standard deviation, that will give you your variance. And these are your steps. From one by one, you have to compute these. And from your variance, you go to your covariance. Your covariance and variance are related in that aspect that when you are calculating your variance, you are only considering the variability of one particular variable, right? One particular geospatial property, whereas in covariance, there are two properties, and you consider how each of them are varying with respect to each other. For example, if one variable is increasing and the other is also increasing along with that, then your covariance is going to be greater than 0. And if one is increasing and the other is decreasing, covariance is negative. If it is 0, then there is no linear relationship. You must have heard of positively correlated variables or negatively correlated variables, or that there is no correlation. So that is again related to your concept of covariance. You just divide your covariance by the standard deviation of both the variables, and then you get your correlation coefficient. Negatively correlated means that it is -1. It is between 0 and -1, and as it increases from 0 to +1, you say it's positively correlated, right? So these are your fundamental concepts. And I was telling you about the pixels, that they are arranged as a matrix. Basically, a matrix is a very good way to represent all your pixel values in a two-dimensional pixel values in a single matrix. And basically, when you have multiple variables, uh, and you have a magnitude of data that you need to compute, or even images are composed of multiple pixels. So even if you have m pixels along the row and n pixels along your column, so that is essentially a matrix of m cross n. And that matrix, that is how all these concepts come into picture, that you need to find out the covariance of each of the variables, or each of the pixels in this case, and you need to compute the covariance of each covariance matrix of that image or that data. And then when you calculate the covariance, it turns out to be a square symmetrical matrix, that is, it is symmetrical across this diagonal. And so this covariance matrix, you can see that the first entry is covariance of the first variable with itself, then covariance of the first variable with the second variable, and so on. And this element is covariance of the second variable with the first one, and so on. So basically, these fundamental concepts are used to do a PCA analysis. And ultimately, the aim of PCA analysis is to reduce the dimensionality of the data for ease of handling, so that we can visualize the dominant patterns and the variability of clusters. We can understand the trends in the data or the outliers, and we can identify the geochemical associations which we can understand from that data we have collected. We can also undertake compositional analysis. So basically, the steps to a PCA are to have a spatial data set, which we have discussed already. We have to standardize each variable, that also we have discussed. Then ultimately, covariance matrix calculation. I had explained all these concepts because I wanted all of you to understand what is meant by a covariance matrix. So then after calculating the covariance matrix, we have to undertake eigen decomposition of that matrix. So after that, we will select the principal components. We will project all our data onto the principal component space, examine loadings, and further analysis. So basically, when principal components are nothing but your eigenvectors. Okay, so if you want to understand what eigenvectors and eigen values are, so we will look at this slide. So basically, if we have any square matrix A, okay, so eigenvectors and eigenvalues are such that they satisfy this equation, right? So that's A minus lambda I times your V vector equal to 0. So V vector, any such V vector and any such lambda which satisfies this equation for a particular A square matrix are said to be the eigenvalues and eigenvectors of that particular square matrix. That this concept is very useful in images. Sometimes people will say that these are your eigenvalues and eigenvectors without really understanding. So this is the basic equation for which needs to be satisfied for any vector to be considered the eigenvector of the particular square matrix. Square matrix can be either image matrix or it can be data matrix. So then basically you have to solve this equation, right? I have just taken arbitrary 3 cross 3 square matrix, and you must be knowing that lambda I will be this matrix, and when you subtract these two matrices, you take this V vector. So this is just an arbitrary example for 3 cross 3 square matrix. And then you have to solve the corresponding matrix equation which comes out from this. And you have, firstly, you have to obtain lambda by setting the discriminant equal to 0 on both sides of the equation. That will give you discriminant of a minus lambda equal to 0. And then you will find out lambda. And then you will substitute lambda and find out your v vector, which is nothing but your eigenvector. So for 3 cross 3 matrix, you will have 3 eigenvalues and 3 eigenvectors. Similarly, for n cross n square matrix, you will have n eigenvectors and n eigenvalues. So now we have completed the eigen decomposition of our square matrix. Now we will select our principal components. Principal components are nothing but your eigenvectors, and you will project your data on the new principal components or the eigenvectors. So now we have to sort our eigenvalues, because the higher eigenvalues will imply more important components, and eigenvalues actually represent the amount of variance captured by each principal component or the eigenvector. So once we have sorted the eigenvalues in the descending order, we will calculate the cumulative explained variance. Cumulative explained variance is equal to summation of lambda k 1 to I divided by summation k equal to 1 to n lambda k. So basically this is cumulative explained variance associated with index I. So that means that if we have to calculate cumulative explained variance for the first highest eigenvalue, we will just take I equal to 1, which means the first value divided by the sum of all the eigenvalues that we have obtained. So, and for the second I equal to 2, we will take the first two eigenvalues and divide it by the sum of all the eigenvalues. Similarly, we will calculate the cumulative explained variance for all I equal to 1 to n. Right? So all the cumulative explained variance, when we have calculated, the next step will be to choose the number of principal components to be retained. So you will see that this is a ratio. This is a ratio of the eigenvalues, and then you have to multiply it by 100, and that value should be between 95 to 98% is the most acceptable value for cumulative explained variance. However, you can choose it to be any value based on your particular application. So once you have selected the value of the cumulative explained variance that you want in your problem, then you can easily determine the value of I. That means you can select how many of the eigenvalues you have to retain. So when you know that, you can understand how many eigenvectors you want to retain. So then we can easily choose the number of principal components that we have in our problem, and we can project the data along those axes, and we can undertake all our geostatistical analysis, or we can undertake all our geological analysis after this. So this basically is the process of the principal component. So I will demonstrate a simple example, and so basically this is the data for some samples, some rock samples that are collected from different locations, and there are major element concentrations and trace element concentrations. So this is the data set that I am using for this particular example only. So so what we can do with this data is that we can undertake the principal component analysis, because it has a large number of variables. See, there are around 29-30 variables that are here, and we need to understand what are the major, we need to reduce the dimensionality of the data. We need to understand what are the major components that contribute to this data for ease of handling and for better analysis. So what we will do, we will undertake principal component analysis. This is nothing but we just read the file, we standardize the data, then we calculate the covariance matrix, then eigenvalues and eigenvectors, right? Then we sort them, then we calculate the cumulative explained variance, and we choose a number of components based on the explained variance, and um, select the first components, and then basically for ease of visualization I have just selected three components that I'm going to be using. So I'm just going to run this, and you will see that there are three axes for the data, that the three principal components are selected. For that, I had to use the desired explained variance as 0.6. So this is your plot, and as you can see, I'll just maximize this. Okay, so this is your plot, and it shows the three principal axes along three directions, x, y, and z. And this is your data, right? This is the data that has now been projected on these three axes, and the dimensionality is reduced. And from here on, we can undertake further geological analysis, right? So this and now we'll continue to the next technique that we will explore, and that is image segmentation techniques. So basically, what is image segmentation? Image segmentation is the process of partitioning a digital image into multiple image segments or regions. Okay, they have to be non-overlapping, and now we will segment, or we will partition the entire image into a collection of connected image pixels. Now we can it is not necessarily only a region. We can identify the linear segments in the particular image, the curved segments. We can segment based on a particular shape, that we want to extract only the circles, or we only want to extract the squares from the image, or we only want to identify the linear roads or such features, or the curved segments only, or only we want to we want to identify particular regions based on some particular characteristics, like in LULC, something like that. So basically, there are all the segmentation algorithms can be basically divided into two types. This is one classification scheme, and the first one is based on the abrupt discontinuity or the changes in intensity, which is basically edge-based algorithms, and the other will be a similarity-based algorithm based on the similarity of pixels of a region according to a predefined criteria. So and then basically the edge based can be anything like Sobel, Roberts, Kirsch, watershed algorithm, and the similarity based can be thresholding, region growing, splitting, split merge, clustering, multi resolution segmentation. And another classification scheme is for you can classify it as your structural segmentations, stochastic, or the hybrid. Structural, the mostly what I will be discussing in this are going to be structural, which are structure based. That we have to identify edges, textures, contours, shapes. So basically, uh, stochastic are probabilistic techniques. Okay, and you just have to model the image as a random process, and based on some particular distributions like Gaussian mixture, the Bayesian probabilities, etc. It's a probabilistic technique, it is advanced and it is computationally intensive. So hybrid techniques will be which use a combination of both of the techniques. So first, we'll come to the thresholding methods. These are the simplest methods, and basically we divide the image pixels with respect to their intensity levels. The selection of the threshold is based on prior knowledge or information of the image features. The first is global thresholding. In this, the entire image is thresholded with a single value of t, which is the threshold value, and that t value is based on prior knowledge. So if the input image is p x comma y and your output image is q x comma y, so q x comma y value will be 1 if the input image pixels value, the digital number is greater than that particular threshold, and 0 if it's less than or equal to that particular threshold. So entire image will be thresholded with that single value of t. And for variable, what happens is that the value of t varies over the image, which is again either it can depend on the neighborhood of that particular pixel, or it can be a function of x and y. For multiple thresholding, again, that multiple threshold values are implemented, and it is basically instead of a single value of t, you include multiple values, and you assign multiple values to your q, comma y, depending on the threshold value. So different types of thresholding result in different types of images, and these black and white pixels that you see basically are dependent on the type of thresholding that you use, and it's based on the specific application or the specific output that you're interested in. So the second type of method that I am discussing is the edge-based segmentation method. So like it is, if you want to identify or you want to extract the well-defined boundaries or the edges from your image. So the first the type of method that we can use for this are your gradient-based methods. So you have your image intensity function across your image, which is basically a function which tells you the intensity or the digital number of your pixel, and then you have to compute the gradient. The gradient means your first derivative, that is d by dx of your image intensity function. You have to compute that, and then depending on the value of that derivative, which is typically highest at your edges will have a sudden change of the image intensity. So it's based, and for some examples can be Sobel operator, Privet, Roberts cross operator, and Shar operator. These are nothing but mathematical functions based on this first derivative. And then you have your canny edge detector. It is a very common method, and it basically identifies the local maxima in your gradient magnitude. So basically, your image intensity will have certain maxima and minima, and then you identify your local maxima in this detector, and it also performs edge thinning and edge tracking for localizing your edges. The third one is your Mehar edge detector, and it's basically a Laplacian of a Gaussian. Laplacian and Gaussian are both mathematical operators, and then first you apply the Gaussian, then you apply the Laplacian to that. So uh, the basic is that the second derivative of the image is taken after smoothing with a Gaussian filter. So the Gaussian filter will smooth the finer discontinuities or the finer details, and then you take the second derivative of the image, right? And you locate your zero crossings. Zero crossings will be they are very effective to detect your edges, and the advantage is that it reduces your high frequency noise because you are smooth with Gaussian filter, and still we preserve the edges. And the other one is zero crossing. Um, uh, Zero crossing points actually correspond to locations. These are different techniques, and in this one you just see where the second derivative changes sign. So if that edge-based segmentation methods are discontinuity-based, and region-based segmentation methods are similarity-based, based on the similarity of pixel properties such as intensity, color, texture, or other features. Again, these are very application-specific. Basically, there are two methods to this. You can either use region growing or region split and merge. So the algorithm goes something like this: that if px comma y is the original image that is to be segmented, and sx comma y is the binary image where the seeds are located. Seeds are nothing but your initial pixels along which you want to grow the region. These seeds are selected based on the prior conditions that you have set already or prior knowledge, and p is your predicate, which is to be tested. You will grow your seeds based on certain similarity condition, based on certain knowledge. That is the predicate. Okay, so and that predicate is to be tested for each x comma y region. That is why you will grow the region based on your seeds. So first of all, the connected components of S are eroded. That is essential because you don't want the similar types of pixels. You want one seed to correspond to one region. And then you compute the binary image PT, where PT x comma y equal to 1 if T x comma y equal to true. That means that if your predicate is true, then your that this new binary image will have the value 1. And then you compute another image where qx comma y equal to 1 if this pt x comma y equal to 1 and x comma y is 8 connected to a seed in S. So 8 connectivity is nothing but that one pixel is connected to 8 other pixels, and this is 4 connectivity. So if so this is the basic algorithm. And for as a simple example, if you want to segment the regions in this, you perform your algorithm, you perform your code in such a way that uh, first you select the seeds in each such coin, and then you define your predicate. Can be based on the intensity values because the background is dark and these are light, so you can give an intensity value as the predicate, that if your intensity value is less than a particular number, then it is true. So this is an example of a predicate. And then it will correspond keep on growing your region for 8 connectivity if the predicate is true in that region. So for region splitting and merging methods, what we do is that the entire image is firstly assumed to be a single region, and then you compute the homogeneity criterion to see if it is true. And then if it is false, it is split into 4 smaller regions, and it is further repeated on the sub-regions until no further splitting is necessary. These square small regions are then merged if they are similar to give larger irregular regions. So this is the type of algorithm or the process that we can follow. And when you set that image and then you extract, then if it is uniform, then you add it to your region list, then you split and add to process list, and so on. So next, watershed based methods. Basically, watershed is a ridge that divides areas drained by different systems, right? So catchment basin is a geographical area draining into a river or reservoir. So when we use watershed-based methods, what we consider is that the catchment basins and the watershed ridge lines in that image are computed by treating it as a surface where light pixels are high and dark pixels are low, right? So when a pixel will have values such as um, 0 or 1 or 3 or 5, then these will be dark pixels. And if the pixels are light, they will have high values like 235 or 225. And if the lighter pixels are high and the darker pixels are low, and correspondingly we can make that image into entire watershed regions. And the differences in the image values, image intensity values, are used to delineate catchment basins and watershed ridge lines. And then those segmented regions are computed based on this analogy itself. And it basically produces stable segmentation and continuous image boundaries. So gray levels, as I was saying, gray levels of the image or the image intensity values are considered to represent altitudes. That is how we can consider the entire image as a watershed region. I'll give you an example for this. And this is an input remote sensing image that I have used. And basically, it is a region where pixels, you can see they have different values. Some regions are dark and some regions are light, and we need to segment these regions based on their properties. There are a lot of different steps involved in watershed-based segmentation, and the entire process can be carried out using any language that you are comfortable with, and this basically involves quite a few steps. I have just put some of the steps for understanding. Like first, we will compute the gradient of the image intensity values. Then we just go on to find out the regional maxima of the regions in which there is uh, a maximum, and the thresholding is done. Then the ridge lines for the watershed are identified, and the segmentation boundaries are also included. And then finally, the segmented regions are obtained. So we can use different types of iterations. So we can refine the process further based on our application, or we can use a completely different way of doing this watershed. It's completely based on your particular application. In this region, this particular region that you see here, the intensity values where they were high, that means that the pixels are very light. Those regions are effectively segmented into some regions here. As you can see, the colors are different, but essentially it gives the boundaries. The colors are based on some of the own algorithms, but actually it gives you all the boundaries of the image, and then you can refine it further. So mostly what the different types of segmentation techniques are used, it's summarized, and basically these are the types of segmentation techniques that are mostly used, and also the advantages and disadvantages are there for both for all these techniques. And for example, you can use each of these techniques based on your particular application. And for example, if you are a beginner and you want to get started, then you can use thresholding because it is quite simple. And however, if you like if for some, if you want stable boundaries, or if you want continuous regions, then you can use your watershed method. And if computational complexity is not any issue for you, and if you are advanced, so then you can use your PD based method or ANN based method, and or edge based method. So all of these have their own advantages and disadvantages. So now we will come to the last topic, which is wavelet transform method. So you must have heard of Fourier transforms. So wavelet transform is another such method. However, it has its differences with the Fourier transform method. So basically, what is a wavelet? You know that a sine wave is a continuous oscillation which extends from minus infinity to plus infinity. It is predictable, it is smooth. Wavelets are some irregular or asymmetric mathematical functions. However, they are very useful for processing audio, images, and other data. So, why is that? That is because they allow localized analysis, because they have limited duration, and they have zero average and varying frequency. So the localization is very well accommodated, and they can capture both low and high frequency components with precision. The meaning of this low and high frequency components I will discuss in the next slide. So, basically, there are many different types of wavelets that are used, uh, and uh, Haar, Shannon, Dobshi's, Corflet, Mexican hat, biorthogonal, Goldner spline. So these are different types of wavelets. They have specific properties, and you can use it based on your specific application. So Haar wavelet might be good for some edge detection maybe, whereas Dobshi's is good for another particular application. And so what is the meaning of this low and high frequency component? So when we use signals, we in Fourier transform we change the domain from time to frequency. On the y-axis there is amplitude, and on the x-axis there is time, and that time is shifted to the frequency domain when we undertake a Fourier transform. So the wavelet transform is such that it will change your spatial domain to your spatial frequency domain. And what is the spatial frequency? That means what is your scale of objects that you are considering, scale of features. So scale of features is represented by your frequency component. And that means that how fast the change occurs in the image intensity function. If there is rapid change in the image intensity function, or there is rapid change within the image, so those will be your high spatial frequency rapid changes, which will be occurring across your edges, across fine details of the image. Whereas if you consider your low rate of change, or very smoothly varying intensity function, or very gradual changes across the image, those will be your smooth regions or your bulky regions, which will be your large scale features, not small scale features, large scale features in your image. And so this is low spatial frequency and high spatial frequency. And now wavelets have this advantage over sine, is that your frequency component can be changed. Now smaller scale and larger scale wavelets, and basically the time, the position and the scale of the other wavelets is changed, and that is how all the variation in the image is very well incorporated uh, by using your wavelet transform. So it will change your spatial domain to your spatial frequency domain and it will incorporate all the different frequency components of the image. So it's a mathematical technique for analyzing and representing images, signals, and data in terms of wavelets. It will decompose your images into different frequency components at different resolutions or scales. So we will have the first like at scale 1, then at scale 2. A level or the scale of decomposition can vary, and when we increase the level of decomposition, different types of coefficients are obtained. So for each level of decomposition, we have four sets of coefficients for the discrete wavelet transform that I'm talking about, which will be your approximation coefficient and the detail coefficients. Detail coefficients are again three types, which are horizontal, vertical, and diagonal detail coefficients, right? So for each level you will have four coefficients associated. For the next level you will again have four. So basically the approximation coefficients will give you the coarsest level of detail. They will smooth the image and capture the overall structure of the image at a particular scale. The detail coefficients for a direction will capture the finer details such as edges and texture variations at that scale. So for the horizontal detail coefficients, you will have your the edges or the finer details along the horizontal direction. And hello सर मेरी चल रही है क्लास अभी ना 2:30 बजे सर मैं क्लास ले रही हूँ अभी ना 2020. So the approximation coefficients and the detail coefficients are there, and the detail coefficients are basically three types. So horizontal, vertical, and diagonal detail. So for the horizontal detail coefficients will give you the details. That means they will give you finer details, small scale variations such as edges and texture variations at that or in that direction. That means along the horizontal direction. Then the vertical will give for the vertical direction and diagonal for the diagonal direction. Approximation coefficients will basically that they will the broad scale or the large scale features that will be given by your approximation coefficients, and then we recursively apply this process of decomposition to the approximation coefficients that we obtain at each level, and hence actually this technique will allow localization in both time and frequency. So this discrete wavelet transform technique, I'll give you an example for this. Um, any image that you can take any image, and then uh, you can apply the wavelets, the any wavelet that you that is suited for your application. You can apply Haar or Dobishi's anything, and then basically that entire there's an entire algorithm. We follow that algorithm. All the steps are followed, and then basically we those the wavelet that we used, the decomposition will give us four types of coefficients: horizontal, vertical, diagonal detail, and approximation coefficients. So with each level of decomposition, the differences in the image will be obtained. Here you can see the image of a particular part of the lunar surface, and not only for lunar surfaces, it can also be done for any particular image for any application, earth-based or planetary, anything. So this example is related for moon. So basically, these particular features need to be identified from the image, like the edges need to be detected. So for that, we are using wavelet transform to detect the edges, right? So the horizontal, vertical, and diagonal detail coefficients for each level. So this is at scale one or level one of the decomposition, right? So you can see that some details are visible, and in the next level, these boundaries are very well defined, and but when we go to scale 3 or level 3, we notice some irregularities, and at scale 4 and scale 5, the information is almost completely lost. You can see that the edges are not very clear. It's very coarse. The entire image is very coarse. So when you increase, so that is how we define at what scale we need to decompose the image to accurately detect the edges, because you see after the scale 4 all the information is progressively being lost. So horizontal, vertical, and diagonal detail coefficients are obtained. Another example is for this region. You can see this region, this particular boundary here, it needs to be detected. So this is horizontal, vertical, diagonal detail coefficients at level 1, and this is the approximation coefficient. So basically the pixel values, you can see these are ranging from 0 to 65, 70, and these pixel values will represent your respective coefficients, like I have mentioned on the top of each image. So they actually correspond to the strength of your frequency component, and basically when you consider your approximation coefficients, they have a smoothing effect on your image. So if you consider approximation coefficient at level 1 and approximation coefficient at level 2, you see that the level 2 is more smooth, and high frequency features across the respective direction are shown by your H1, V1, D1 and H2, V2, D2. So if you see here, there is no detail that is visible at this level. Then you again apply the decomposition again to your approximation coefficient, and you obtain your H2, V2, D2, and A2. So from here, you see that some features, some of the boundary is slightly visible, and we will see this again in your level 3 and level 4. You will see that actually these were bunch of craters here, right? So this is completely smoothed over. And even in this region, there were quite a lot of small scale features which are completely smoothed over, right? So this has a smoothing effect, which is progressively becoming more and more as your level of decomposition is increasing. And that this boundary that you see here is not visible at all is becoming progressively more and more visible. That means this coefficients are in such a way that we can easily identify the boundaries. So finer details become more visible as level of the decomposition increases, right? So you can see here, this is the this is the boundary, and this is level 6 and level 5. So beyond this level, the decomposition is not required because all the details are lost. And you can see here how coarse this image is appearing, and uh, this detail is progressively getting lost in the as we increase the level of decomposition. So thank you.